I really would like to thank the organizers for organizing such a nice workshop and for inviting me to it. I find it very exciting. I would like to shed some new light on the connection of primordial black hole dark matter and the LIGO Virgo observations. And so we, like everybody of you who has watched some of the talks by now knows that black holes can form in the early universe when you have order unity fluctuations on the horizon scale, and they form at horizon entry, since then is the point where they feel their self-gravity. And there are simple arguments like scalings, which you see there, which can explain that. This has been known from the 60s to the 70s and has been found by the authors down here. And they also realized that as the universe is radiation dominated and the speed of sound is large, that this can only occur against pressure forces. So it's a fine balance between self-gravity and pressure forces. Now, my collaborator Jens Niemeyer and I were actually very interested in this phenomena of primordial black hole formation. And so in the 90s, about more than 20 years ago, we decided to do numerical simulations on this process. And I believe they're the first which had been done. And we had several questions. One of our questions was, accretion on black holes had been called upon potentially making the black hole go as fast as the horizon of the universe, which would mean that the black hole would engulf the entire universe or a large part of it, which would, of course, be catastrophic. And another question was that phenomena and critical phenomena in general relativity, which had been discovered a few years before, which implied that when you're close to the formation of a black hole at the threshold of it, that there's a scaling relationship of the black hole mass. And we want to know if this can be applied as well in the early universe, and indeed it could be applied. So here on the left-hand side, you see a simulation slide, which shows you an initial perturbation. And as essentially there's enough time that it feels its own self-gravity, we could see that the strong pressure wave is moving out, a black hole is formed in the center, and that accretion wasn't critical. The black hole formation process would be quickly finished with no much further accretion. And here on the right side, you see that the scaling relationship actually, as predicted in optical phenomena, holds very well when you get close to the threshold for black hole formation, which is the case when you have Gaussian fluctuations, since only very few volumes can collapse, horizon volumes can collapse to form black holes, to not overproduce dark matter. And so this could be used to compute the mass function of black holes much better than before. Now, my personal interest in this came also from another subject, and that was that at the time, the Macho collaboration had found some fraction of the halo could be made out of objects which were unidentified, objects of the order of 0.5 solar mass, and which couldn't have been white dwarfs or stars. So I noted in '97 that when you during a phase transition, actually, like, you have a reduction in speed of sound. Here in particular, I was considering a first order phase transition at the QCD epoch, because at that time it was possible that it would have been first order, we didn't know yet. And I argued that this effective speed of sound is going to zero during the transition, which means there would be no pressure forces. And that this would imply that the QCD horizon would be a preferred mass scale for forming black holes. Preferred because if you have a roughly scale invariant spectrum, it is easier to form them during the QCD epoch. I also noted that higher order transitions or annihilation periods would have a similar effect. So we did simulate this fully general relativistic, and in this plot here, which is less colorful than the plot before, because I made it, you can see that an initial fluctuation starts to collapse, a black hole forms at some point, and at some critical moment, between here, this is the energy density as a function of radius, essentially. Like at some critical moment, anything which goes into this mixed state of a first order transition just collapses immediately right away to the high energy density phase. And so you had actually a bias to form black holes there because there are no partial forces. And here you can see the critical threshold, how much overdensity you have to have in like delta rho over rho. So you see it's of order unity. And when you go far away from the transition or further away, it is high. And when you were like having regions collapsing at the transition, it is lower. And since for an exponential, like Gaussian statistics, essentially, not exponential, like this would give you a huge enhancement of black holes on this scale. Now, the modern version of this is as follows. By now, due to some gigantic effort of people doing lattice gauge simulations, we know the equation of state essentially all the way from the temperature of a few hundred GeVs all the way down to the current temperature, unless there's some other surprises. And the QCD equation of state, the QCD transition is not a first order transition, it is a crossover. But that doesn't make a big difference since there is a drop in the speed of sound and also a drop in the pressure over energy density. And similarly, there is also, of course, a well-known drop in the pressure at the E plus E minus annihilation, as well as there is a small drop at the electroweak transition. And those drops occur whenever you deviate from essentially ideal gas, relativistic gas, whenever some of your energy is in form of interaction energy, as in the case of the QCD epoch, or the rest mass, like those components which do not contribute to the pressure. So borrowing results from Burns et al., they use this equation of state to compute via analytic methods. Those are not full general relativistic calculations, but they probably should come close to the result. They use those methods to compute the critical threshold for black hole formation and then convolve this, given a certain spectrum, to derive the mass function of primordial black holes. Here you see the solar mass scale. So you predict around the solar mass scale for roughly scaling invariant spectrum, you will have a peak, like about a factor 100 more black holes than on other scales. And of course, it goes up here a bit too. I want you to put your attention on this shoulder here. This shoulder is an enhancement on the scale of around 30 solar mass, the scale which LIGO Virgo first detected black holes to be existent. And this comes to a shoulder which is here, which is like when pions essentially are annihilating. And so there was a lot of activity around primordial black holes, and primordial black holes are a perfect cold dark matter candidate. However, there are two subtle differences compared to particle dark matter, and both of the subtle differences will play an important role in my study. The first one is that primordial black holes start their lives at essentially zero peculiar velocity. So, I mean, the other difference is that the individual dark matter particle mass compared to particle dark matter is large. And the first difference, the close to zero peculiar velocities, implies that the formation of very eccentric binaries occur. First, the black holes form at some epoch, and then at some later stage, even before radiation matter combination, radiation matter equality, at some later stage, you form binaries which are very eccentric, and that's easy to understand since the velocities are essentially zero. The two black holes feel each other's self-gravity and just go radial inwards and would almost want to coalesce immediately if it wouldn't be up for maybe a third or fourth black hole to have some tidal forces. So the distribution was found even as early as 1997, and then reused in 2016, was found to be very eccentric. Where the eccentricity is like essentially like very close to 1 usually. And the coalescence time, the merging time, which would give you the gravitational wave signal, is proportional to a factor which, when the eccentricity goes to 1, the coalescence times gets very small. And if you convolve this, then you would see here the fraction of black hole binaries, which of all the binaries, this fraction which coalesces at the time 10 gigayears, which is typically of the order of 10 to the minus 9, but has this huge enhancement factor here due to the eccentricity distribution, which gets it more to the order of 10 to the minus 3 to 10 to the minus 2, which was implying that 30 solar mass primordial black hole dark matter have merger rates which are too large, a factor 100 at least too large than those observed by LIGO and Virgo. When you go to the right side here, like this initial distribution was actually also used by the LIGO-Virgo collaboration themselves to derive limits not only on the 30 solar mass scale, but derive limits if all the dark matter would be in the order of solar mass. And the limits you can see here, this is the region allowed, of course, and the signal was expected to be here, so that it was concluded that neither 30 solar mass nor 1 solar mass primordial black holes could be the entire dark matter. And see here, like there are dots, 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 because this has been studied by probably altogether on 10 papers and restudied, with the conclusion holding up that this is like not changed by any other tidal forces in the universe or even the existence of clusters. That was the state when I came into the field. I was busy with non-scientific things for a few years. And I started seeing this and being an outsider, not being part of it. I was baffled that people would believe that binary with an eccentricity as high as that, which is the peak of the distribution, would actually survive. Wouldn't just the simplest, smallest interactions, a simple tug on this binary make it slightly less eccentric and then scattered out of the coalescence band. So the second difference, which plays an important role in my study, is that primordial black holes have essentially additional isoquadratic density fluctuations just simply due to Poisson fluctuations in the number of black holes in a given volume. So this implies that formation of primordial black hole clusters at very high redshifts occur. And you can see here on the right, those clusters are very dense. They have densities well beyond the density of a globular cluster. And you can see from this beautiful paper of Inman and Ali Ahmoud, which did numerical simulations on this process, you can see that clusters even at a redshift of 100 already exist. Here is a blow up. This cluster must probably, I don't know, it's hard to say how many members, but for sure not 10 or 100. There's an easy way to estimate the formation redshift of such clusters, and the densities is just simply essentially plus Schächter with this initial perturbation thing. And clusters, however, do not survive if they're too dense. We know from globular clusters that they have a finite lifetime. And that is because a cluster which, in the cluster, a cluster member once in a while gets a tiny bit more energy than on the Maxwell-Boltzmann tail. And since it's localized the cluster, it can leave the cluster. And that's something which you cannot undo anymore. And so clusters shrink, better expand with time. And this evaporation time is something which is known in standard textbooks. And you could see that, for example, clusters forming with 100 cluster black hole members would form roughly at a redshift of 300, but would evaporate at a redshift of 15. And roughly, of course, and even though they had very large densities, they are disappeared by now. Keep in mind, a cluster of the order of, which has of the order of 1,300 members would have formed around a redshift of 100, a bit below, and is evaporating just currently. That is the estimate of this standard textbook equation. So I was interested to numerically evolve the binary taken from this initial eccentric distribution the interaction between binaries with a single black hole in the cluster at the densities which were predicted. And I did a full Monte-Carlo simulation of this process, taking into account only the most important scattering events, like the 10 to 100 most important scattering events, where importance would be gauged by how close the single black hole gets to the binary, and taking into account that the clusters would actually only exist for a certain time between the formation and the evaporation time. So here are four kind of just randomly picked interactions where I show all initial binaries which had an initial coalescence times of 10 gigayears, and those are 30 solar mass binaries, and a third 30 solar mass single black hole coming in. What you see in those plots is here, as a function of time, you see the relative distances. So here's the distance between black hole number 1 and 2. Here's the distance between number 1 and 3, and 2 and 3. So you see essentially this is the binary here, reflects the binary. And you see also that a single black hole comes by and doesn't even get as close to the binary as to be able to go into the orbit, then goes out again. Nothing dramatic seems to happen. But if you look at the exact numbers, what happened here is that I started with an initial eccentricity of this very, very large value. And the final eccentricity was just by this tiny tug taken a bit down, which implied that the initial merging time of 10 years, 10 gigayears had moved to 6,000 gigayears, so a much larger number. In other situations, you would see like more complicated orbits. I find them quite beautiful, actually. And you see like how essentially the binaries exchange partners over and over. Here it stays, but it changes properties, then partners are changed, then the partners are changed again. Well, here's a bit of a mess. Well, the end result often would be that the initial coalescence time would move from 10 gigayears to around 10 to the 10, 10 to the 11, 10 to the 14, 10 to the 7 gigayears, so far away from observations. So having done then complete Monte-Carlo simulations on the process, where I take what is shown here is the effect of several, like 10 to 100 most important scatterings in a cluster of 100 members over the lifetime of this cluster. And you see here that here you see the final semi-major axis as a function of the initial major axis. And those lines here, they will always guide you for equality between the two, AF equals AI. And you see here that the semi-major axis actually changes for hard binaries to lower values, and which implies that the coalescence time becomes lower. So the inverse effect than before. But however, the eccentricity, again, here's the final eccentricity essentially over the initial, it's really 1 minus e squared. Like this value, it's not eccentricity, it's like 1 minus e squared. Those initial values here of 10 to the minus 4 to minus 3, which give you this really short times, would go up to very high values. And the net effect would be that the 10 gigayear binaries from this initial distribution would mostly be scattered to around 10 to the 10, like to a higher mass. Like there are exceptions, of course. You know, this is a statistic process. You know, there are ones which go to lower coalescence times too. So if you keep in mind that this process, like of cluster formation, is also occurring as process of hierarchical structure formation, as we are all well used to, then small clusters form first with very high densities, and they are also, of course, the building blocks of larger clusters, which are then the building blocks of even larger clusters. So the small clusters here at some point evaporate, and they evaporate into the large cluster, and they make up the environment of the large cluster. And this process continues. So when you take into account the membership of black holes in small clusters, which then go into bigger clusters, which then go into bigger clusters, you find that essentially the effect of this disruption is the same from all cluster generations. And that is because even though small clusters have much higher densities, they live much shorter due to evaporation. And it actually is like the larger clusters in terms of number of black holes, which are making a slightly bigger effect. So here you see like the results. You see the fraction of binaries coalescing at time t, and here is 10 gigayears. And you see that is the result without clusters. And you observe that like there's obviously suppression. And if you combine all of those, then you get a very large suppression of the black hole merger rate at 10 gigayears. So like my conclusion was that the LIGO Virgo observations most likely do not roll out that all of the dark matter is in 1 or 30 solar mass primordial black holes. There is a loophole. There may be the occasional binary which has never entered any cluster, and that's something which needs to be studied. So that sort of changed the picture for me a bit, because those constraints seem to be not relevant. And now I asked myself, well, okay, but then, you know, the black holes do not make up the signal of LIGO Virgo. That's not very attractive either. But I realized other people have written papers about this before too, but in different environments, not in those clusters which were talking about. And like I realized that there is the possibility of direct capture. Just two single primordial black holes in present-day clusters could directly capture, essentially get captured by gravitational wave losses, and then very quickly would merge. And I was certainly interested to compute the rates, because I knew, like, well, I think, you know, I'm pretty sure that the current primordial black hole sits in a cluster with 1,300 members. I know its densities, I know its velocity. So I started going with a scenario where you have an inflationary peak, so nothing with the QCD phase transition, inflationary peak, which gives you most of the black holes on the scale of 20 to 30 solar mass. And I was able to compute the rate. And you see the result here. Here's the merger rate at 10 gigayear. And here is as a function of the number of PBHs in the cluster. And I've told you that clusters around, this is of course a rough estimate, you know, below 1,300 roughly did evaporate. And those clusters larger, they still should exist at the current epoch. And you see that the merger rate actually goes quite nicely through the upper and lower limit, like which is determined for the rate determined by LIGO Virgo. So that was very encouraging. And I asked myself the question, what happens if I actually like have solar mass black holes, like inspired by the QCD equation of state, mostly solar mass black holes? Are they ruled out? And I was able to compute via the same expression as shown before that, again, like even in the case of solar mass black holes, they are not ruled out if they're all in clusters because, well, and the initial binaries are essentially made much less eccentric, because LIGO Virgo is still not efficient enough to observe them currently. So I found out rates. Here is again like those are evaporated. I found rates which are factor 10 lower than what LIGO Virgo upper limit is. Maybe in the future one could observe them. The next question was, well, what happens like with the large like holes merging, which have been found the 30 solar mass roughly, like this is always because there's a range around, of course. And like I realized, like when I assume a QCD inspired scenario where the 30 solar mass black holes actually like make up a fraction of the order of 1% of the dark matter, as you have seen in the plot before from the mass function, then I realized like a simple thing to realize, this is all really simple physics in the end, that the velocity of those heavy black holes would be smaller than the velocity of the solar mass black holes because of equipartition, and the heavy black holes would sink to the center. The sinking to the center would enhance their density at the center, so they would have a much higher fraction than the 10⁻² at the center, and the velocity would also enhance their direct capture rate and their merging rate. And so when I computed like this standard physics problem, I found that the merger rates again do roughly just cross into the band of between the lower and the upper band, like as determined by LIGO Virgo. And so that was very encouraging, of course. The next question was, well, LIGO Virgo has also observed black hole binaries which were very asymmetric in mass, in particular one, GV 190814, which was the merging between a 2.6 solar mass black hole and a 22 solar mass black hole. So 2.6 solar mass black holes said wrong because we don't know if it's a neutron star or if it's a black hole. It actually does fall somewhat in the forbidden mass gap. It seems to be too heavy to be a neutron star and too light to be a black hole. That doesn't mean that it's not explainable with standard stellar physics and evolution of populations. But it was interesting. This object was a bit of another surprise again. So when I did go through the calculations to have the rate, compute the rate in those clusters between the heavy black holes and the light black holes, I came up with this. Like, again, the rate did match quite well for the clusters of which are larger than around 1300, the naturally predicted number. The rates would fall into the rough range where LIGO Virgo estimated the rates. So let me step back and tell you that I believe that this is highly non-trivial because there were no free parameters. There is one free parameter, and that is what is the abundance, what's the fraction of dark matter the black holes make up. And I fixed this just to 1, because if it would be lower, there wouldn't be many clusters. I fixed it to 1 by Occam's razor. Once I have done that, I can predict all the merger rates with some pretty easy standard book physics. The scale of 30 solar mass is predicted by the QCD equation of state. The merger rate is predicted. It is predicted why solar mass binaries have not been observed yet. And the merger rate of asymmetric mass mergers is also post-predicted, I would say. And so this gets me to my conclusions, and I don't really have to go read over them in detail here because I hope you just heard the talk. And I can only tell you that recent observations by nanograph is a pulsar timing array, which seem to have found some signals, not clear if it's gravitational waves, but some signal which could be consistent with gravitational waves, seem to lend credibility to such a scenario because it comes right at the frequency where those black holes would be forming, and the amplitude seems of the right order of magnitude. What I've not talked about so far is that on piece of paper, microlensing constraints by errors do exclude this range for dark matter. But I would like to ask the community to revisit this problem, because after all, if you think about it, the macho collaboration had found a signal. They had found between 13 to 17 events, and they were at odds with errors, which had not found a signal. They had not found a single event towards the LMC. The Pointer-Agapi collaboration has also found events which is consistent with what Macho found. And I believe this is not the end of the story. And I was very, very happy to hear yesterday from Surhat that Subaru has the potential to go into this range. And I would strongly urge them to do that if it's not too painful. Okay, I think you're here.
Okay, thank you very much, Karsten. We have time for a couple of questions. Are there any? I don't see any in the chat at the moment. I'll just ask.
There's a raised hand. There was a raised hand.
I don't. Okay, is there a raised hand? I don't. Oh yeah. Okay. Bernard Carr. Bernard has a question. Please, Bernard. I will unmute you. Go ahead.
Thank you very much indeed, Jedamzik. It's you were the first person who studied these QCD black holes, so it's really great you're the person who may be saving them, in the context of LIGO observations. But the question I wanted to ask, though, in most of these scenarios, you do predict an actual mass function for the primordial black holes. I mean, you showed how the equation of state changes. So if you put in a very specific mass function, you do predict what the relative number of black holes is in the different mass ranges. You seem to be doing the calculation, for different masses for the black holes, but we do actually expect the black holes to have a mass function. So what happens if you put the mass function into your calculation?
Yes, and that is a very good question, and that is things which need to be done in the future to really like put a mass function in there and do more detailed simulations, and that is something I would love to do. The estimate I'm giving here is, of course, a very rough estimate in terms of the mass function, because I assume it to be bimodal. Yeah, like I assume essentially 99% to be on a solar mass and 1% on 30 solar mass. That is a very, very rough estimate, and definitely like could be improved and will be improved. I want to improve it,
And of course, as regards the lensing constraint, micro lensing constraint, which, as you say, is really crucial. I mean, as most people will know, that is very sensitive to the clustering of the black holes, because if the black holes are sufficiently clustered, you can avoid or at least reduce the micro lensing constraints.
That is a thing which is up in debate. There are papers out which say like when black holes are in clusters, that essentially the whole microlensing analysis doesn't apply, because one wouldn't see the individual black holes, but the entire cluster. I think this has to be studied in more detail. But it is really true that there are a lot of smoking guns for such a scenario. And the only way which may stay in the way right now, only thing which may stay in the way is microlensing constraints. And since there was not a dispute, but disagreement between the results of Macho, Point-Agape, and Eros, I do not right now believe that there should be written 100% into stone. Of course, this may be wishful thinking.
And the supernova microlensing constraints are also important, of course, because they also might seem to exclude it.
The supernova microlensing, yeah, absolutely. Yep. There's also the
yeah,
but there are also other papers which claim that the microlensing, if you vary like your halo mass a bit towards what's still allowed, but a bit towards extreme ends, that you still could be consistent. So I think there needs to be some more work done. And like I said, I would be very, very happy to see more observations from, for example, Subaru, confirming that also the Nancy Grace Roman Space Telescope will also perform microlensing in a revolutionary way. I think there may be a surprise there.
Thank you.
But yeah, thank you.